I would like to begin with an introduction to some simple differential equations. Differential equations are something that you have encountered before, either in your Calculus 1 class or Calculus 2 class, so I would like to start with some familiar examples. All differential equations really come from mathematical models. They come from observations about the real world in which we're trying to understand how things change. And so we take those observations, which are in words, and we turn them into differential equations with symbols. So I'll start with something that's pretty simple, which is Newton's laws of motion. So we're going to let y of t be the position of a rock that is thrown straight up from a starting position of y0 with some starting velocity, we'll call it v0. Okay, so imagine that there's going to be some rock, and what we're going to do is we're going to throw that rock straight up in the air so that there's only one dimension to our problem. Well, as we throw that rock straight up into the air, there's a force that's pulling down on that rock. And that force is the force due to gravity. So there'll be some force due to gravity, which is pulling down on that rock. And we want to just describe the motion of that rock over time. So the way we can do that is to use Newton's laws of motion, and in particular, use the fact that the acceleration due to gravity is a constant. Okay, that constant is called g. It's 9.8 meters per second squared. And if you're throwing the rock up, and we're thinking about up as being the positive direction, that acceleration is felt in the negative direction. So that acceleration, we'll call that negative g. Okay, but acceleration actually relates to the position of that object. Okay, acceleration is the derivative of velocity, and of course velocity is the derivative of position. So really acceleration is the second derivative of position. And so what I've written down for you is that the second derivative of position, second derivative of y, is minus g. And this is actually a differential equation. It's an equation that has derivatives in it. There's some other pieces of information in this problem that were important. There's an initial condition that says that y of 0 is going to be some height, we'll call it y sub 0. And v of 0 is going to be some initial velocity, we'll call it v sub 0. And given those initial conditions, and given this differential equation, I believe that you can find y of t. So you should take a moment right now and ask yourself, if I know the second derivative of a function, how can I find the function itself? So pause and see if you can figure out what the function y of t is. Assuming that you've paused and tried this out for yourself, we're going to now solve this together. Okay, so I have the second derivative, which is minus g. So why don't I find an antiderivative, and that will tell me what the velocity is. So if y double prime of t is minus g, then y prime of t must be minus g times t. And of course, there should be some sort of arbitrary constant, because if I take the derivative of that constant, it's going to be 0. Now, what is that arbitrary constant? Well, I know what v of 0 is, which is, of course, velocity is the derivative of position. So I know what y prime of 0 is. And y prime of 0 is c if we plug 0 into this equation. But y prime of 0 is also supposed to be v sub 0. So c must be v sub 0. So I'm going to go ahead and replace c with v sub 0. So now I actually have an equation for the velocity. Okay, now that I have that, what about position? Well, I can play the same game again. Okay, so I'm going to find the antiderivative, y of t. That's going to be minus 1/2 gt squared plus v0 is a constant, so the antiderivative there is just t. And then I need to add another constant. And just to be careful, I'm not going to use c because it's supposed to be a different constant, so I'll use the letter d. And then to determine d, I'm going to use the initial condition. So y of 0, if we plug 0 into this equation, we get that y of 0 is d. But of course, y of 0 is supposed to be y sub 0. So in fact, d should be y sub 0. Okay, so now I have my answer. Y of t is going to be minus 1/2 gt squared plus v sub 0 t plus y sub 0. And so this equation describes the motion of the rock over time. Okay, so if I start at time 0, okay, what I have is an upside down parabola. So I'm going to assume here that y sub 0 and v sub 0 are both positive, so that the rock is starting in a positive position and that we're throwing it upward. But what I have is, because of the negative sign in front of the t squared, is a parabola that opens up downward, like that. Okay, so and that gives us our graph of y of t versus t and the motion of that rock. And so now we've solved our first differential equation. And that's probably the easiest differential equation that we'll solve all semester. And we probably won't solve a lot of differential equations like this because you probably did these problems in Calculus 1 and in physics, and they're really not the interesting differential equations problems that we could be looking at because the answers are pretty straightforward. You just have to anti-differentiate. So let's look at some more complicated models. And what we're going to do in order to motivate new types of differential equations is we're going to look at other types of models, and we're going to turn those words into equations again. So we're going to look at some simple growth decay models. So we're going to look at population growth, and we're going to make a simple assumption. The change in a population, P of t, is proportional to the population size. Okay, so there's some key words here I want to look at. First is the change in population. Okay, we want to understand how a population changes. Okay, and then it's proportional to something. And what is it proportional to? It's proportional to the current population size. Okay, that current population size. Now, first of all, does this assumption make sense? Well, imagine we have a population of bacteria. Okay, if you have a population of bacteria, those bacteria divide. So the more bacteria that you have, when they divide, the more new bacteria that they make. So the change in population is proportional to the current size. Same thing works with people. The more people you have, the more reproduction that can happen, and so the more new people that you will end up with. Okay? And populations don't have to grow just from reproduction. We can also talk about populations as being a population of a group of people that have a certain disease. Okay? So if a group of people have a disease and we want to see how the group with that disease is growing, we can say the more people that have the disease, the more likely that they're going to spread that disease to other people, and so the more growth that we're going to have in the disease. Okay, so let's take these words and turn them into a differential equation. First, we're going to look at the change in the population. So ask yourselves, what represents change? Well, one thing that represents change, or one way to write change, is a derivative. The derivative of P tells you how the population P changes over time. So the change in population we're going to write as dp dt. Now, that change in population is proportional to something. Oh, it's proportional to the current population size. So it's proportional to just P, the current population size. Now, what does proportional to mean? When two quantities are proportional, what we're really saying is that one of those quantities is a constant multiple of the other. Okay, so in this case, dp dt is a multiple of P because it's proportional to P. So dp dt is some constant, I'll use the constant K, times P. And so we've now taken these words and we've turned it into a differential equation. Okay, so here P is the current population, and then K is the constant of proportionality. Okay, so dp dt is K times P. And this is actually a very different differential equation than the one that we encountered before. Before, what we had was that the derivative of y was a constant, or in this sense, a function of t. Okay, so the derivative of y here was a constant function of t. But now we have that the derivative of P is actually a function of P itself. And so the techniques that we used before to solve this differential equation aren't going to work because we can't just integrate the right-hand side because we don't know what P is. There is one more piece of information that's kind of implicit in this description, and that is we need to kind of know where the population starts. Okay, so we also need to know what P of 0 is. So usually if you're given one of these problems, you'll be given some sort of initial population. We'll call that initial population P0. Okay, now we've taken a description, a physical description, and we've turned it into a simple differential equation with an initial condition. Let's look at some other ones. Okay, so we're going to read this again. We're going to have the decrease in the amount of a chemical. Okay, so that's kind of a rate of change. We're going to see that it's proportional to something. It's going to be proportional. What is it proportional to? Oh, the amount of chemical that's left. Okay, so how do we want to write that? Okay, so the decrease in the amount of chemical decreases a rate of change. Okay, it's going to be proportional to, it's going to be constant times. But because it's a decrease, I'm going to say explicitly that constant is negative. And then it's proportional to the amount of chemical that's left. Well, how much chemical is there to begin with? Oh, C. Okay, so we have dc dt is equal to minus K times C. Using that physical description, we'll also add an initial condition. C of 0 is equal to some initial amount of that chemical that's decaying. We'll call it C sub 0. Okay, and this differential equation, the only difference between it and the one above is the population growth. The K constant there is positive, and so we expect that population to grow, that rate of change to be positive. Chemical decay, we expect that that's going to be a decrease in the amount of the chemical, and so that constant K is negative. But notice that I put the sign in for k. I put the negative in there because generally when you write these differential equations down, you want to know which terms are going to be positive and which terms are going to be negative. So you assume that the constants are all positive, and then you put in these signs. Okay, how about compound interest? Well, interest is a rate of change. It's how much is being added to an investment, and that rate of change is proportional to the current balance. Okay, so interest is actually the rate of change of an investment, ds dt. It's proportional to, so there's a constant k, and it's proportional to the current balance, which we'll call S. And then if you have some sort of investment account, it must have some sort of initial amount that you stick in there. Okay, and so this is a way to express compound interest on an investment as a differential equation. Okay, so all three of these differential equations were similar in that they basically all have a derivative is equal to a constant times itself. Okay, these are going to be some simple growth decay models. I want to also make them a little bit more complex. Okay, so I want to add some more terms. So first I'm going to look at what happens when the population of a town has, say, no natural growth. So the population isn't going to grow for that particular town. Nobody is going to have a new child. Nobody's going to die. Okay, but that town is losing citizens at a constant rate, L people per year. So people are just moving away at a rate L per year. And how would I express that as a differential equation? Well, that population is going to be changing. So we're going to have dp dt. And what we're saying is that population is going down at a constant rate. Well, that just says that the derivative is a constant minus L. And of course, that population is going to start at some initial amount. We'll call it p sub 0. So if there's no growth rate going on and we're just losing people at a constant rate, that just says that the derivative is minus L. Now, again, that's not much of a differential equation. Okay, we could certainly find the antiderivative, p of t, if we like. Okay, and if you did a little bit of work, you would see it was p0 minus lt. And that would be a very boring town to model. Okay, but there's a principle here that's important, and that is understanding, okay, if you have constant loss in a system, then we want to say that the derivative is minus a constant for that constant loss. Okay, so what does that have to do with some of the other models that we were looking at? Well, what if we were to have a town that grows at a rate k? So a town is going to grow at a rate k. So dp dt is going to equal to k times p. But then that town is going to lose people at a rate L. The way that we do this is that we combine the two differential equations that we had before. So first we had the growth, dp dt equals k times p. But then we had the loss at a rate L per year. So we just combine them by putting minus L here. And so now we have a town that's growing at a rate proportional to the current population, but also is losing citizens at a rate of L people per year. And so now we have a slightly more complicated differential equation based on the scenario that's described to us. Again, I'm going to put in an initial condition here. P of 0 equals P sub 0. Okay, let's look at a similar model. What if a drug is being absorbed in the body? Okay, so the concentration of a drug is absorbed by the body at a rate K proportional to the current amount of the drug. Okay, so we got a rate of change for the amount of the drug. Okay, so we're going to do dc dt because that's the amount of the drug, and we're going to look at the rate of change. We notice that that rate of change is proportional to the current amount of drug. So it's equal to minus k times c, and it's negative because that drug is being absorbed into the body, so we're taking away from that concentration of the drug. But now the drug is going to be added back, maybe through some sort of IV that's hooked up to the person that's streaming in that drug. Okay, and so it's going to be added at a constant rate of I per hour. So if we want to include that constant rate, we'll just add I. And so now we have a drug that's being pumped in, maybe through an IV into a person, okay? And then the body is absorbing it at a rate proportional to the amount that is currently in the body. Again, we'll have some sort of initial condition, C of 0 equals C sub 0. And so these two models here are a little bit more complicated, and we're going to work with them a little later in the week this week. So hopefully this gives you a sense of how you can take a physical description and you can turn it into a differential equation. We'll be studying all of these models that you see here. We'll be studying them throughout the week and learning how to understand certain characteristics of these differential equations and eventually how to solve them. So now that we've put together a bunch of differential equations, let's look at some terminology for differential equations. So what is a differential equation, or a DE for short? It's an equation involving one or more derivatives of a function. Okay, so we've seen some differential equations like the one here for the drug absorption rate. Okay, it's an equation that has one derivative and it also has the function itself in it. Okay, we also saw, if I scroll back up, the Newton's law of motion example that had a second derivative in it. Okay, but again, it has a derivative in the equation. Okay, now we're going to be studying this semester ordinary differential equations. That's a differential equation that involves derivatives in a single variable. So most of the time, the variable that we're going to use is going to be t, because we're really usually interested in rates of change over time. And so time will usually be the variable that we're working with. And so our differential equations are only going to have that one variable, time. Now, we do offer a course after this one called partial differential equations, and that's a differential equation that has, instead of regular derivatives, it has partial derivatives in more than one variable. So maybe we want to understand what's going on in time and in space. So we'll have multiple variables like t and x. Okay, so we have something called the order of a differential equation. And the order of the differential equation is the highest order derivative. So if I go back up to my example here of drug absorption, I have a first derivative there. And so the order of this differential equation is 1. If I go back up further to the Newton's law of motion example, I have a second derivative. And so the order of that differential equation is 2. We're going to start by studying first order differential equations, where the highest derivative is the first derivative, but we will move on to higher order differential equations with second derivatives and so forth. Now, the solution to a differential equation, as we saw with that first example, is not a number, it's actually a function. So the solution is going to be a function, y of t, that satisfies the differential equation. So that means that both sides are equal when you substitute your equation for y of t. And we're going to see some examples of that later. But basically what we're going to have is an equation that relates the derivative of a function likely to the function itself, and we want to be able to substitute in the derivative of the function and the function itself into the equation and make sure that both sides are equal. And that's going to be a solution. Now, if you have a differential equation with initial values, like some of the ones that we have seen, That's called an initial value problem. So if you have a differential equation with an initial value, with one initial value or multiple initial values, we call that an initial value problem. And generally, those are the problems that we're going to be solving because they're going to represent some sort of physical phenomena, not just having an equation that relates the rate of change, but we need to know where things start. Okay, so a well-posed problem is a differential equation with an appropriate initial or boundary conditions that guarantee the existence of a unique solution. So basically, we want to take these physical observations and turn them into well-posed problems so that we can write down a differential equation with some appropriate initial conditions. And then from that, if it's a well-posed problem, then we can guarantee that there's a solution to that problem, that we can find out, okay, what is the population going to be over time? What is the concentration of the chemical going to be over time? What is the position of the rock going to be over time? So we want to be looking at solving well-posed problems. Okay, so let's look at solutions to a differential equation. So most of the initial value problems that we're going to start with are going to look like this. dy dt is equal to f of t and y of t. And y of t sub 0 is going to be y sub 0. So we have a differential equation and initial condition. Notice that the right-hand side of the differential equation is a function of t, the independent variable, and y, the dependent variable. Our first example, that function was just a constant, or we could think about it as a function of the independent variable t. But these recent examples that I've done about population growth, those were functions of the dependent variable, okay? And so we can have the right-hand side be a function of both of those. Now, it turns out I can tell you right now what the solution is going to be. It's going to be y sub 0 plus the integral from t sub 0 to t of f of s y of s ds. So essentially, just like that first example where we needed to find an integral to solve the differential equation, it turns out that this general differential equation here, the same thing is true. The solution is just an integral. Now, why is that true? Well, let's look at what the derivative of y is. The derivative of y, dy dt, is equal to, okay, the derivative of y sub 0, that first term right there, the derivative of that term is 0. Okay? Oh, okay, now we got to take the derivative of that integral. So think back to your calculus class and think about the fundamental theorem of calculus. Oh, the derivative dy dt is actually f of substituting in for s. We're going to substitute in t, which is right there, the upper limit of integration. And then we're going to substitute in t in the second part too, y of t. Oh, look, dy dt is f of t and y of t. So the derivative does match our differential equation. And that was true by the fundamental theorem of calculus. Okay, but that tells us that we have found the solution to the differential equation. But we want to know the solution to the initial value problem. So the initial value problem needs to be true as well. Okay, so we're going to do y of t sub 0. Okay, y of t sub 0 is going to equal y0 plus the integral of t sub 0 to t sub 0 of f of s y of s ds. Okay, so what happens when you integrate something from the lower limit t sub 0 to the same thing for the upper limit, again, t sub 0? Well, that integral has no area underneath it, and so that integral is 0. Oh, so what does that tell us? Y of t sub 0 is actually y sub 0. So we have verified that this function that I've given you, this integral, okay, is a solution to the differential equation because the the equality holds. But also, it's a solution to the initial value problem because y of t sub 0 is actually still y0. Okay. So, now I've told you, okay, here's the solution. It's just given by this integral. So is that it? We done? Is that all we have to do? Is an integral, which we learned back in Calc 2. So is it just that simple? And the answer is no, not really. And the reason why is because this function that we need to integrate is f of s, y of s. But y is the thing I'm trying to find. Y is the unknown. And so what I'm saying is that the solution is the integral of this unknown function. So in practically speaking, we cannot find this integral. It's not going to be something that we're going to be able to easily find. So the answer is we're going to have to look at some more sophisticated techniques if we're going to solve these differential equations. Okay, so it's not going to be as simple as just doing an integral.